All right, welcome everyone. Today we're going to build a really deep understanding of how our skeleton, your very own skeleton, is formed. We're going way beyond the basics to explore the two surprisingly different and frankly brilliant architectural plans our bodies use to construct bone right from the ground up.
So this whole process is called ossification, or osteogenesis if you want to get fancy. And it's not a one-size-fits-all deal. Depending on where the bone is and what it needs to do, your body, like a master architect, picks from one of two totally different blueprints. So let's kick things off by looking at what makes them so fundamentally distinct from each other.
Okay, let's lay the foundation. To really get a grip on these processes, we've got to start with the where and the what. Where in the skeleton do they actually happen, and what raw materials are they starting with? The answers, as you're about to see, are completely different, and they set the stage for absolutely everything that follows.
Okay, so right off the bat, this slide gets to the heart of it. It all comes down to the why. On one side, you've got intramembranous ossification. This is for building flat bones. Think your skull, your clavicles. It works directly from a kind of primitive embryonic tissue called mesenchyme. It's almost like 3D printing bone right where you need it for fast, strong protection. But on the other side, there's endochondral ossification. This is for our long bones, your femur, your humerus, and its method is totally different. It first creates a perfect little miniature model out of flexible hyaline cartilage, and then it replaces that model with bone. So why the cartilage model? Well, it's brilliant, really. Cartilage can grow from within, which allows our arms and legs to get much, much longer, something that just depositing bone directly can't do.
Let's dig into that first pathway, the more direct one, intramembranous ossification. This is the body's go-to method for quick, no-nonsense construction. It's absolutely essential for forming those protective plates of our skull while we're still developing, and it's also the process that kicks off healing when you fracture a bone.
So what's the big takeaway here? No middleman. Seriously, no cartilage whatsoever. This process builds bone straight from a sheet of embryonic tissue called mesenchyme. And mesenchyme is incredibly versatile. It's what's called a precursor tissue. Think of it like a kind of cellular clay that can turn into all sorts of things, muscle, cartilage. But in this case, it gets the direct order to become bone.
This slide shows the entire construction sequence, and it's awesome. First up, step 1. A chemical signal tells these mesenchymal cells to cluster together and transform, first into osteoprogenitor cells and then into the dedicated bone-building cells, the osteoblasts. That cluster? That's your ossification center. Then in step 2, these new osteoblasts get right to work, secreting this unmineralized, protein-rich matrix called osteoid. As they build, some of these workers actually get walled into their own creation, and that's when they mature into osteocytes, the bone maintainers. Step 3 is where it all hardens up. The matrix mineralizes as calcium salts are deposited. Blood vessels start weaving their way in, bringing nutrients and forming a network of spongy or trabecular bone. And finally, in step 4, the outer surfaces get remodeled into a dense, protective layer of compact bone. And just like that, the structure is complete.
Okay, to really get what's happening in step 2, you gotta understand osteoid. It's basically the scaffolding. Before you pour concrete, you have to build a rebar frame, right? Well, that's osteoid. It's this organic matrix, mostly made of incredibly strong type 1 collagen fibers, all laid down by those osteoblasts. It gives the bone its initial framework, a little bit of flexibility, and it's the perfect surface for hard calcium and phosphate minerals to latch onto and crystallize, creating that rigid, strong bone we need.
All right, so we've seen the direct approach. Now let's switch gears and look at the more, intricate method our body uses for the vast majority of our skeleton, especially the long bones that let us move and, most importantly, let us grow. This is endochondral ossification, and it is a true masterpiece of biological engineering.
So the magic word here? Transformation. This whole process is all about replacement. The body doesn't just build bone out of nowhere. First, it creates a perfect, detailed model of the future bone, but it makes it out of hyaline cartilage. This template is genius because, like we said, cartilage can grow from within. It's called interstitial growth, and that's what allows our bones to get significantly longer as we grow from a kid into an adult. Then, over weeks and months, that entire cartilage model is systematically broken down and replaced piece by piece with bone tissue.
Now this pathway is definitely more complex, and this slide maps it all out. It all starts with that cartilage model, formed by cells called chondrocytes. Then, in step 2, things get dramatic. The chondrocytes right in the middle of the model swell up, that's hypertrophy,
and they start to calcify the matrix around them. This actually cuts off their own nutrient supply, and as they start to die, they send out a chemical flare, a distress signal called VEGF. This triggers step 3, vascular invasion. Blood vessels bust into the deteriorating cartilage, bringing a whole new demolition and construction crew. Osteoclasts show up to clear away the dead cartilage, while osteoblasts form a bony collar around the shaft and start laying down real bone inside. In step 4, those osteoclasts keep on carving, hollowing out the central medullary cavity for bone marrow, while new secondary ossification centers pop up at the ends of the bone. And, super importantly, step 5 shows that a thin slice of cartilage is left between the ends and the shaft, and this becomes the all-important growth plate. So, have you ever wondered how you actually got taller? Well, this right here is the engine behind it. The epiphyseal plate, or growth plate, is what drives our vertical growth. And it's not just a simple layer. It's a highly organized little factory with different zones. You have a resting zone, then a proliferative zone where cartilage cells multiply like crazy, like stacking up coins. Next, in the hypertrophic zone, they swell up, and finally, in the last zone, that old cartilage is systematically destroyed and replaced by bone coming up from the shaft. This whole process literally pushes the ends of the bone further and further apart, making it longer. It's only at the end of puberty, when hormones stop the cartilage production, that this plate finally turns completely to bone, fusing everything into one solid adult unit.
Okay, putting them head-to-head like this really makes the differences pop. Intramembranous starts with simple mesenchyme and just deposits bone directly. It's fast, it's efficient, it's protective. Endochondral starts with a complex hyaline cartilage model and replaces it. It's a slower process, but it's built for longitudinal growth. One builds flat bones, the other builds our long bones. Even the role of blood vessels is totally different. In intramembranous, they just kind of weave into the bone that's already forming to give it support. But in endochondral, their invasion is the critical, transformative event that kicks the whole replacement process into high gear.
So, we've seen the 2 different blueprints. Now let's pull the personnel files on the specialized construction crew. We've seen them on the job site, but if we take a closer look at their individual roles, you'll see just how incredibly coordinated this whole project really is.
All right, here's the full lineup, the whole cast of characters. We start with the mesenchymal cells, those super versatile stem cells that are the origin point for our builders. Then we have the chondrocytes, the cartilage specialists who work exclusively on the endochondral pathway. And then, of course, you've got the main bone crew. The osteoblasts who build, the osteoclasts who demolish and remodel, and the osteocytes who stick around to maintain the finished structure.
First up, the builders, the osteoblasts. Their lineage is pretty direct. A mesenchymal cell gets a signal to become an osteoprogenitor cell, which is basically committed to the bone-making life. That cell then matures into an active osteoblast, and these guys line up on any surface where new bone is needed, and they have one mission and one mission only, to build. They secrete that osteoid, and then they manage its mineralization into hard bone.
And then we've got the demolition crew, the osteoclasts. And what's really wild about them is that they're not even related to the builders. They come from a completely different family of cells, the same one that produces our immune cells. These huge multinucleated cells latch onto the bone surface and form this little sealed-off zone. Inside that zone, they create something called a ruffled border, which massively increases their surface area, and then they pump out acid and enzymes to literally dissolve the mineral and digest the matrix. This resorption is absolutely vital for hollowing out that marrow cavity and for allowing our bones to be reshaped and repaired our entire lives. So what about the builders who get walled in? Do they just retire? Nope, they become osteocytes, the live-in superintendents of the bone. Once they were active osteoblasts, but now they're encased in these little chambers called lacunae. From there, they stretch out these tiny little arms through channels in the bone called canaliculi, and they connect with each other, forming this incredibly sophisticated sensor network. They're constantly monitoring mechanical stress and strain, and they can send signals to the builders and demolition crews on the surface to direct repairs or add reinforcements. They are the true guardians of our skeletal integrity. Right, so this amazing cellular crew doesn't just show up empty-handed. They use a really sophisticated biochemical toolkit full of enzymes, signaling molecules, and of course, raw minerals to get the job done. This here is their biochemical toolkit. We've already talked about osteoid, that's the collagen framework. Of course, you need the raw materials, calcium and phosphate, the mineral building blocks that form those hard hydroxyapatite crystals. But just as important are the managers and the messengers. You have critical enzymes like alkaline phosphatase that help the hardening process along, and you have signaling molecules like VEGF that act as chemical dispatchers to coordinate the whole project. So let's zoom in on alkaline phosphatase, or ALP. Think of this enzyme as the site foreman.
It's secreted by both osteoblast and those swelling chondrocytes, and its job is to prep the construction site from mineralization. It does this by cranking up the local concentration of phosphate. But maybe even more importantly, it neutralizes a chemical called pyrophosphate, which naturally stops mineralization from happening. So ALP basically comes in, clears out all the chemical roadblocks, and paves the way for the bone to harden.
And remember that chemical flare we talked about? The SOS signal from the dying cartilage cells? Well, this is it, VEFG. As those chondrocytes are starved of nutrients, they release this molecule, which acts like a super powerful magnet for nearby blood vessels, basically yelling at them to invade the dying cartilage. And that vascular invasion, that is the absolute turning point, because the blood brings in the osteoclast to clear the debris and the osteoprogenitor cells that will become the brand new bone builders.
And check out this number, 99%. That's how much of your body's total calcium is locked away in your bones. It just highlights how important bone is for way more than just structure. Ossification isn't just about building a frame. It's about creating a secure, dynamic bank for almost all our calcium and a huge chunk of our phosphorus. And this mineral bank is constantly being drawn from and deposited into for countless other critical things. Every muscle contraction, every nerve impulse, every single heartbeat depends on the precise regulation of calcium that our skeleton makes possible.
Which brings us to a really fascinating final thought. Why have two completely different methods? Why evolve a quick, direct build pathway for our skull and this slow, methodical replacement strategy for our limbs? It really reveals a biological system that is just incredibly optimized, using the right tool for the right job. You have a rapid build process for immediate protection, and you have a scaffold-based process that allows for complex shaping and the longitudinal growth that's so essential for movement. Our bones are not just inert structures. They are dynamic, living tissues, constantly being built and rebuilt by two of nature's most elegant architectural plans.